Welcome back to another thrilling video lesson presented by me, Mr. Calmy. Today we're going to talk about half-life reactions to start off with. Half-life reactions are identified by the amount of time needed to react 1/2 of the reactants from the original amount. If you look at the table, or I guess the graph, you'll notice that the half-lives are laid out for you. If you originally start with 150 of the original reactant, this happens to be a reactant that is in pressure. Remember, pressure and molarity can essentially be interchanged. And this is the first instance where that happens. So you've got 150 torr or pressure units and then 75. And what you're looking at is how much time it took in order to make that first half disappear. Now, it's about estimated to be about 14,000 seconds. So if you're given a graph, just simply look at what you start with, cut that in half, extrapolate over, determine what time on the graph intersects that particular concentration or pressure in this case, and you'll have the half-life, which is an amount of time. It's usually represented by T to the and then subscripted 1/2. That means half-life. Now if you look at the second half-life, which is the amount of time it takes to go from 75 to 37.5, which is half of the original, then you'll notice that it takes about the same amount of time. And what that means is that half-life, this is about 28,000 seconds. So it doesn't take a rocket scientist to realize that the half-life for this type of reaction is the same. The half-lives are equal, 14,000 seconds. You would suspect the third half-life to be another 14,000 seconds, and at that 14,000 seconds you would have half of 37.5. Now, it's important to note at this time that half-lives for first-order reactions identified or can be calculated using the following formula. The T1/2 is equal to 0.697 over the K constant. This formula is included on your formula sheet that's on the back side of your periodic table and will be given to you for the AP test. It's the only half-life formula that you need to know, and it's important to remind you that it only is true for first-order reactions. For zero-order and second-order reactions, in fact, the half-life formula is not constant, and it's can only be calculated using data. In other words, what you have to do is use the differential rate law or the integrated rate law, which is what we talked about in last class period, and take the initial concentration and the final concentration, which would be the half of the original. And you'd also have to know the K constant in order to calculate time. Or you could take the time and calculate the K constant, but you gotta have one and calculate the other.
A couple more things to add to half-life for first-order reactions. And the one thing that I want to point out is that half-life is independent of the concentration. But this observation is only true for first-order reactions. That's not to say that the concentration isn't important for a first-order rate law. In fact, first-order rate law, when you double the concentration, the rate doubles. But for half-life, when you're calculating how long it takes for half of the original concentration to disappear, that is independent of the original concentration. So if you double the original concentration, the half-life still remains the same. If you triple the original concentration, the amount of time to get down to half of the original concentration is constant. And the last thing I want to talk about first-order half-life is that it can be applied to all radioactive decay problems. So if you encounter a radioactive decay problem on the AP tests like you did in last year's test, 2018, my students weren't necessarily prepared to answer this because it wasn't clear to me, but it is now clear to me that all radioactive decay is considered to follow first-order relationship for half-life.
This is a type of question you would see that pertains to half-life reactions and half-life questions. Maybe something from a mixed practice or something coming up on a quiz or test. It states in the question that the reaction is indeed first order. You have to know the order of the reaction in order to determine what formula you're going to use. You will be told the first order, second order, or zero order. And if it's a first order reaction, you can use the formula that we just outlined on the last slide if you indeed need it. Now, this one wants you to just estimate the half-life based on the graph. So what you want to do is you take, okay, so I've got 0.1 to start. Now, where is it down by half? Well, I'm going to go over and I'm going to determine where upon this line that 0.05 molar intersects at what time. And it looks to be about 350 seconds. So T1/2 is about 350 seconds. Now that you know the time, you can calculate K. Calculate K for this reaction. And so back to our formula, T1/2 equals 0.97 over K. Well, you can plug this in for T1/2, 350 seconds equals 0.697 over K, and you can solve for K. Switch spots with K and 350, 0.697 over 350 seconds, and that's equal to 1.99 times 10. Oh, actually, I can do this. Let's scroll over. Give myself some room. 1.99 times 10 to the -3rd seconds to the -1 power is the unit on that K value. In summary, as you can notice, the half-life equation for a first-order reaction is independent of the concentration. It only depends on what K is. If K changes, then the half-life of that first-order reaction changes, but the initial concentration doesn't affect it. Furthermore, each half-life is the same. The first half-life, or the first amount of time it takes to reduce the concentration by 1/2 the first time, is the same as the half-life it takes to go from 1/2 to 1/4 of the original concentration, and then 1/4 to 1/8 is the same half-life, and so on and so forth. For a second-order half-life reaction, the half-lives get twice as long as the lifespan as the one before it. So if the first half-life is 50 seconds, then the second half-life is 100 seconds, and the third half-life is 200 seconds. And so the half-life doubles each time a subsequent half-life is measured. It doubles the half-life each time. Now that's an observation that might come in useful on an upcoming quiz or test.
Well, that takes care of this little video lesson on half-lives. Thanks for listening.